There's one seat here. There's a seat here. Second row. 0th row also has a seat. Okay, I want to start. Please, there are a couple of seats here, row number 0, and I see a backpack sitting there. The backpack is not participating, so someone can sit there. And another seat here in the middle. So okay. I'm going to actually start 3 minutes after 12:30 under the condition that you'll be seated already 3 minutes after, so we can actually start. There are 2 seats here, row 0 and 1 there. Okay, so I want to just remind you where we are, and we have a lot of policies that I described last time, just to put it on a slide. Some of you, I know, haven't looked at the web page. All this information is on the info page, on the web page. Note also that you have a schedule page that is an approximate schedule to when we're going to do what. Not final, but pretty good approximation to what we're going to do, including tentative date for the midterm and the final that we're planning now to have in class. There are going to be notes on the web page that we're going to update, and there's Piazza that many of you, about 2/3 of the class, are already on it, so we'll try to communicate with you. Do listen to what I'm saying here and ask questions here, if possible, because, as I said, a lot of people have the same question. A lot of people ask the same question on Piazza, so it's going to be effective to do it here. Okay. Details, now that these details are correct, TAs, office hours, and discussion session that we're going to start on the 3rd week of the semester. Please come to office hours. What else? A few other details. We already issued homework 0. Hopefully, most of you have looked at it. And one final comment on registration. So I already know that a couple of you managed to register. I have a waiting list of all the people that sent me email. All of you should have seen a response for me. If you haven't seen the response, come after class or send me another email. I think all of you should have seen it. Okay, so, and again, I want to say, if you know that you're not going to take the class, or if you registered somehow, please let me know so I'll have an updated list. Questions? No questions. Excellent. Okay, so last time I gave you this handout on the badges game that is supposed to be a puzzle in learning. So really an example of something that we're going to do this class, most of what we're going to do in class, which is supervised learning. And I wanted you to think a little bit about it. I know that several of you actually figured it out during class. And again, I don't want to get the answer yet. I just want to know who knows, who thinks that they have the answer. Ah, not enough, which means the other ones haven't looked at it, because I know that you can solve it. So please take this seriously. It's an interesting thing. It will get you to think about learning. And this is why you're here. So look at this stuff. I'm going to talk about it now, but it's a lesson for the next puzzles that you're going to see, and you can even think about this one. Okay, so before we get to these things, this is what you see there. You see training data. You see a bunch of names with pluses and minuses next to them. So interpret it as a positive and negative examples. For example, Naoki Abe was a positive example, Eric Baum was a negative example. The story behind this really happened over 20 years ago. Actually, I was a graduate student, so you could see my name on that list. There was a machine learning conference, and the program chairs gave this puzzle. They put pluses and minuses on the badges of attendees, and the question was, what function was used to assign these labels? So I assume some of you know what function was used to assign this label. Before you tell me what it is, I want to tell me, how do you know that you know? We started with this last time. There was a suggestion. Who gave the suggestion last time? Okay, give me yeah. What did you say? Fits all the samples. So that good? Is that enough? Good start, yeah. Yeah.
It's also very short.
Okay, that's much better. Why is this an improvement over the first suggestion? Yeah?
You could literally make a list of all the names that are...
Right. So it's rather easy, in this case, to be consistent with the data. But it doesn't generalize, right? That's not what I want. What I want is I want to have some predictive power. Perhaps what I want is, given this list of names, to be able to add pluses and minuses on them. That indicates some predictive power. Perhaps all I want is just to know what function. These are two not exactly identical tasks, but related tasks. But definitely just being consistent isn't sufficient. Okay, so what else do we want to know about this task? So we already said that, you know, there are at least two questions I can ask. I can ask you to predict, and I can ask you to model. Give me the function. Before we get to details, which problem was more difficult? Yours, the one I gave you, or the one that was given to the people in the conference? People in the conference. Why? What did... They could not see everyone at the same time. That's one source of difficulty. And you could see all the examples. Maybe they didn't even see all of them. Yeah?
They also didn't know that was it just...
And so I told you the way I presented the data indicated that it's the name. The way they saw it on a badge. It could be the shoe size of the participants, the school they go to, their height, many other things. I actually selected features for you. I told you it really depends only on the name. I still didn't tell you what is it in the name. What's the answer? Someone that knows the answer. Yeah.
The first two letters, first is a consonant.
Okay, the suggestion here, look at the first two characters of what? Of the first name. And?
If the first letter is a consonant.
If the second is a vowel, do we really need that the first one is consonant, or? Just the second is a vowel. It's true also with the first is a consonant, but that's actually a very important point. Your function and the other function are actually different. So I could find a name on which they will disagree. This name is not in the list, and therefore your hypotheses are consistent on this data, but may not be consistent on future data. Remember this. This is really important. So we have a simple function. Moreover, you're sure that it's the right one because it's so simple. Now, say again the function. Okay. What is a consonant? What is a vowel? Is it part of your input? What I gave you is a string with characters. So it's okay for the function to depend on characters, location of characters, length of the string, whatever. But your function depends on something being a vowel. What is it? What is a vowel? Yeah?
Vowels of a set of A, E, I, O.
It's a specific set of 5 characters. You know it's called a vowel. If instead of being a vowel, I would tell you, I would define a function that depends on X, Z, M, D, E. Same function. Second character is one of this set of 5 characters. In what way will that change the problem? Change the problem. Let's start with, will it make it easier? Why not? It's the same function. The second character belongs to this set. Yes or no? Why is it more difficult? Sets, same size. Well, yeah?
The one set is meaningful to people and the other one is not.
You brought some background knowledge with you to solving this problem, and one of them, because you know it exists somewhere, someone has named it, it's a natural set, under some definition of natural, it fits your definition of this is a short definition, right? This is what you were looking for. If it was this second character is one of these 5 things, it wouldn't be as short and perhaps not as convincing as an argument for I found it, right? So again, this is something I did not place in the input. You figured it out, and you actually used it as a way to convince yourself that it's a good solution. Conciseness. So this has to go with background knowledge. A lot of times, background knowledge is essential for us to actually solve learning problems. Which also indicates that learning, we're talking about learning as a kind of an abstract notion here, you did not learn a lot from this data. You actually learned a lot before you saw this data. And then you brought this knowledge, played with it a little bit, and learned this simple definition of a concept. Now, if you were to program this, what would you do? Write a program that will be given this data and will produce a function or will produce predictions for these people. How do you go about doing it? Questions, any ideas? I mean, all of you would do something if I give you this as a puzzle, so, yeah.
Reading the list.
What you suggest is a program that verifies that his function is correct, whether it's consistent with the data. But how would you find this function? Yeah. What does it mean to infer patterns? Yeah, I mean, that's what you want, right? I mean, we agree on that. You want to infer patterns, but let's be a little bit more concrete. How would you go about doing it? Yeah.
I would try to
Okay, so re-represent the input somehow. Will that give you this solution? Yeah?
Before you can verify that something
Good. So you want to entertain a set of functions that could be candidates, and then you want to look at the data and verify for each function whether it's consistent with the data as a first necessary condition or not. What set of functions would you consider? Yeah.
so the number of positives and
Could have been something with the size. Could have been a lot of functions. I mean, I don't want to suggest a number now. I'm going to do it a little bit later today in a simple case. But think about how many options are there here. Just looking at positive and negative is a good thing to do, but not discriminative enough in this case. Okay, so instead of combination, I would call it properties of the input. I will entertain a bunch of properties of the input. Starts with A, starts with B, starts with C, starts with D. Second character is A or B or C or D. Third character is A or B or C or D. First two characters are AB or BC or AZ and so on. Length is 1 or 2 or 3 or 7, or the length of the first word is length of the second word here. A lot of properties that this can have, and then the question would be, you can enumerate, probably thousands of properties of this. Some would make sense to you, some would not. Some would not be consistent with the data, some will be consistent with the data. These are properties that we call features, and this gets us closer to thinking about this collection of functions that you wanted to define. Any other suggestion? Okay, so next week you're going to solve this problem, write a program that will solve this problem even before you know anything about machine learning or learning algorithm or anything, because we're going to give you a tutorial for how to program with learning algorithms. So essentially the learning algorithm is going to be given to you as a black box. You will only use it. You will not know yet what's inside. This is what we're going to do later. But next week you'll be able to, hopefully, within an hour, write a program that does this. Later on you'll see some more sophisticated versions of this. But the idea is that it's not so trivial if you try to think about it, unless you've done it before, to think about how do I go about writing this program. So that's what we want to do in this class. And let's start to think about or sort of introduce the key notions here. So the protocol that we are talking about, the one that I gave you on this piece of paper, is something that we call supervised learning, right? So we want to think about systems that at the end infer some function or induce some function f that map input strings of names, for example, in this case, x, to some output y. So I'm going to give you a collection of x's drawn from some space of examples. In this case, the space is going to be all possible names of people. And I'm going to map it to some output y. In this case, it's going to be positive, negative. And I'm going to do this mapping via some function that is hidden from us, f of x. That's the idea. So we deal with this collection of algorithms or systems, because there's more than just the algorithm, that perform this mapping. Why do we want to use learning? In most cases, as I gave in as I showed last time, the reason we want to do learning is because we don't know how to program it. We really need to look at examples. I mean, this is kind of a boring example, this badges game, but a lot of the example I've used last time, even the simple example of part-of-speech tagging, given a sentence, what are the nouns, what are the verbs, what are the adjectives, you just don't know how to write a program that does it without considering a lot of examples and have the problem induced from examples. So that's our protocol. We're going to call the collection of x's the instance space. We're going to call the collection of possible y's, in this case binary, the label space. And we have a target function. This is the function we're looking for. We are going to learn another function, g of x. And hopefully g of x is going to be close enough to f of x. What do I mean by close enough is something that we'll have to think a little bit about. But you already saw a very good example of it this morning where we actually had two functions. One of them had to do with the first two characters of the first name. Another one had to do only with the second character of the first name. From some practical perspectives, the functions were the same because on the data I gave you, they were the same. But we both agreed that these are different functions. There are some inputs on which they behave differently. So think about this g of x and the target function that you may never know, and how would you tell whether you got it or not. So eventually, the core of the system is going to be a learning algorithm. This learning algorithm is going to get a bunch of training examples, pairs, x, comma, y. X is the instance, y is the label, and is going to produce a model, g of x. We will assume, and we're going to talk about this in more details, that there is some distribution, D, that governs the generation of training data. And we will also assume that these examples are independently generated from this distribution. But these details do not matter for us now. But what's interesting to think about is that the only protocol that you can think about? Or can you dream up other learning protocols with the same items that you can see here on the slide?
How about predicting a new item into a data?
Okay, so that's a new task. You say, I mean, give me another x that makes sense, given that I've seen these pairs. Is that what you mean? Yeah, that's a legitimate task, but not supervised learning. I'm talking now about supervised learning, so I know that my algorithm is going to get pairs x, y's. Here, I'm defining a very specific protocol. Suggestion?
I can make it interactive if you can model it.
Okay, so the interactive, or I'm going to call it online learning. So here I gave you all the data at once, capital N examples, and you looked at it, or your learning algorithm looked at it and produced some model. You could say, I'm going to give you the examples one by one. I'm going to give you x1, comma y1. Think about it. Make a prediction. Once you make a prediction, I'm going to tell you whether you're right or wrong, and then I'm going to give you the second example, and so on. This is a little bit more similar to the situation perhaps people in the conference faced. We will see actually that it doesn't matter so much. All the theories and all the understanding that we're going to develop for batch are going to apply for online and vice versa. In fact, online is going to be, in many respects, easier to think about. Once we have a model, we want to test it. So one option for us is to reserve some label data for testing on the side, something that you've never seen or your learning algorithm hasn't seen before, and something like this, pairs, again, of x, comma, y's. But what I'm going to really give you is only the x's, and expect that you will produce the y's. Your algorithm will produce the y's. So I'm going to apply the model that I learned to the test data, this g of x, produce some g of x i's, and then compare them. I'll have some metric based on which I'm going to compare x and y's. So again, you can ask yourself, is this comparison between g of xi and yi the only way to test? Or can you think about other ways of testing? Any other suggestion for testing? Yeah? Right? So this is some kind of a cross-validation procedure, which we will do. But conceptually, it's very similar to this, right? Still, I set aside a bunch of test examples, and I decide whether I'm good or bad based on comparing the prediction g of xi's on the yi. Let's say if I get 90% of them correct, I'm going to say, I'm pretty happy. This could be one thing. Maybe you're more strict, you want 99% correct. But you could imagine something else. You could imagine that, I actually am not going to look at predictions at all. I'm going to look at the function g itself. And I'm going to compare it to the function f, assume I have it. So I just want to look at the functional representation. I want it to be exactly this. It's not sufficient for me that it behaves well on this test sample, because the test sample was also drawn from some distribution, and maybe tomorrow I'm going to draw something else and it's not going to do well. I really care about exact learning. So you can see situations where you really care about exact learning. You want to make sure that the function that you've learned is the function. Yeah.
What would be an example of a situation where you care about?
Also formal testing, for example. So people are using in programming languages where they want to formally test the program. They want to learn properties of programs. And it's very important that what they've learned, induced from data, is exactly what's needed. They don't care about statistics. This would be one example. There are other examples that people really care about learning the function. Now, it's a tricky protocol. Sometimes the learning protocol that they will use in these cases is not exactly the one I have here. In addition to just examples, they may require that the input will have other inputs. For example, maybe the input, the protocol itself is going to be interactive. They are going to query the learning algorithm. What would you say about this example as part of the learning protocol, rather than just supply the learning algorithm with examples? So we're going to give some examples, actually, in the next couple of weeks of different learning protocols that are more natural for this give me the exact answer case. Yeah? Of course we do. We're going to talk about it. Yeah. Okay, but this is one case. There's actually, you can even think about other ways to use the test data. Right? So I gave you already learned, now I give you test data. Just the x's. Of course, one way, as we said, to use it is to evaluate g of x on it and see how well you're doing. But you could dream up other ways of using this test data. Yeah?
Determine the domain and the range of the functions?
You can learn something about the domain, and maybe, I don't know about the range so much because I'm only giving you x, but certainly about the domain. Another suggestion?
Can we modify g of x by looking at?
Why do you think you can do this?
We're getting more information.
Yeah. So that's actually, I mean, these two ideas together are what I was looking for. So essentially, you know a lot more about the x's you might see, that you might care about. And sometimes, even without the labels, it gives you information that you could use. This is sometimes called transductive learning. We're not going to talk a lot about it, but it exists. But intuitively, you could feel that knowing what are the problems you're going to be tested on, as students, you know that this is helpful, even when no one gives you the answers. right? You know something about the distribution of the test, and this could be useful. Okay, so hopefully this gives you a little bit of insight into the badges game that we talked about, even though we don't know how to write an algorithm yet. But that's what we are starting to develop now. This is just a reminder of the list of topics that we're going to cover. And unless there are any questions, we can start. Questions? No questions. Okay. So we're talking about supervised learning, given a set of examples of some unknown function f. We want to find, at this point, I'm going to say a good approximation of f. We'll have to make this more concrete. X for us is some representation of the input. It's not necessarily the two words that I gave you. Perhaps the two words are not a productive representation, and I want to convert it to another representation. And this conversion to another representation is one of the key processes in learning, because it's essentially the process of entertaining what could this function, f, that I care about, what could it depend on? Right? So does it depend on the length? Does it depend on the number of words in the string? Does it depend on the last character, the first character, whether it's a vowel or not, a lot of other things. So this is a feature extraction step that is key, ill understood, in the sense that we don't have good theory for this, but very, very important. So we are going to model X somehow when we talk about learning algorithm abstractly, and we can model it either as Boolean vectors, 0, 1. We can model them as real-valued vectors. And our target function, the Y that we care about, could be either binary, positive example or negative example, as in the badges example, but or -1, +1, same thing. It could be a multi-class classification, so choose one of k values, and it could be a real-valued function. So essentially, everything that we're going to do is going to apply to all these paradigms with almost no change. You can take any example that you want that is listed here, or any of the examples that we talked about last time, and think about it this way, as what is the input, how do I encode the input, what is a good encoding of the input, and what is the Y. Now, it's important to realize that a lot of prediction problems, when you first look at them, they don't look as classification problems. But really, I don't know, think about, instead of the example I'm giving here, think about, automatic car, driving an automatic car, or writing a program that drives the car. But really, if you think about it, it really is composed of a lot of classification problems, just like those that we are talking about here. So what are the issues we want to talk about? So this is really one of the most important slides in the not only today, but in the class, just because it lays the ground for what are we going to talk about. And there are really three issues. One is modeling. The second one is representation. And the third is algorithms. As I said last time, most people are excited about algorithms, but everything really depends on modeling and representation. So by modeling, I mean, how do I actually take a problem and formulate it as a learning problem, as a machine learning problem? How do I represent the data? And which learning protocol do I use? Specifically, where do I get the labels and how do I get the labels and the data from? The issue of representation is really important. What kind of functions do I want to entertain? Right? We talked about it a little bit this morning, but we actually did not converge to a function or to a set of functions. But this is going to be important. So this is one level of representation. What functions? The second aspect of representation is how do I represent my input? Do I represent my input as just the string? As properties of the strings? What properties of the strings? This is an important representational issue. And also, of course, what do we know in terms of theory? What are rigorous ways to think about these things, or general approaches to think about these things? And finally, algorithms. So we have to not only to come up or study algorithms that people have invented, but we want to also think about what are good algorithms. How do we define success of a learning algorithm? As I said before, we don't just want to produce the labels on the training data. Just a function that gives me back the list of names with pluses and minuses next to them is uninteresting. I want to be able to generalize to future previously unseen examples. So the issue of generalizing versus overfitting just to the data that I've already seen is a big issue here. And of course, there's a computational problem. We are computer scientists. At the end, we want to know how expensive is it going to be for us to do the learning? Is it going to be computationally efficient? Is it intractable? Can we say something about complexity of learning? And we're going to say things about all these things. So these questions are exactly the same question in here, only that now I'm using a little bit of more terminology. Instance space. This is the space of X's that we are dealing with. So what is our instance space? What is our label space? The Y space. What is the hypothesis space? So by hypothesis space, I'm going to call the set of all functions that we are considering as candidates for a target function. There are a lot of functions. We're not going to consider all of them. For example, you did not consider any function that depends on the height of the person carrying the badge. Right? So you limited yourself to specific functions. Moreover, you somehow limited yourself to simple functions under some definition of simple that we may want to come up with. And we will come up with as we go along this semester. And of course, what learning algorithms we use. And how do we evaluate the learning algorithm? I'm using here the terminology of loss function. So how do we measure success? Measuring success is important both when you evaluate yourself, and it's also important when you decide what's going to drive your learning algorithm. I'm going to learn in order to do what? To minimize the number of mistakes I'm making, or maybe some other metrics that I want to do. So these are all questions that we're going to start addressing today. Instance space. This is one. So the instance space, as I said, is this collection of X's that I'm going to map using G to a collection of Y's. And it's going to be very important to design an appropriate instance space. So it could be Boolean, 0, 1 vectors. In the example of spam email, Boolean feature could be things like, does this email contain the word money? Or does it contain the word? But you could also think about real valued features. How many times does the word money occur in this email? Okay, and in the case of badges, here are some features that you may want to consider in generating the instance space, in generating the set of features that you want to map the string to. Once we have it, we actually mapped the input X into some vector space, right? We represent the string Eric Baum as a collection of properties. Think about them as dimensions in a feature space. So X becomes a feature vector somewhere here. And we're going to start thinking about learning as doing something in this vector space. For example, when I'm looking at the second letter as one of the features, I'm going to represent Naoki as 1 and the rest zeros, and so on. I can think about the ith letter. So I can take a group of 26 characters for my first group of features, whether the first letter is A or B or C or Z. And then I'm going to look at the second letter, another group of 26 numbers, and the third character, and the fourth character, and so on. And eventually, this is going to give me a vector representation of the name with respect to a specific mapping. mapping the text, the characters, and their position in the name into account. Now, as I said, you could have proposed a different set of features, and you will get a different vector representation, but you're going to get some vector where the coordinates of these vectors represent properties of the input. And this is really what your learning algorithm is going to work with. Okay, you're going to do this a lot this class, so this is now an introduction. But it's really important to know, to realize, and hopefully this example is sufficient for you, to convince yourself that good features are essential. If you were not choosing the character and their positions in the string as features in the badges example, you will not get it, because this is really what the function depends on. If you were just looking at lengths of strings, height of the people, you know, their university and so on, without caring about characters and their positions, you wouldn't be able to get this function. Is that clear? So features really, really are important, and it's really domain specific. So this is, again, one of the key secrets in machine learning, that features are really important. You will see later that it's important not only because it gives you the chance of solving the problem and it encodes understanding of the problem, but also computationally. A lot of the computation, if not the vast majority of the computation, actually goes in practice on the steps of extracting the features, mapping from the input that you see to this vector representation that your learning algorithm is going to see. Label space seems simpler. In most cases, we're going to just think about the label space as binary features. But sometimes it's going to dictate which learning algorithm or which type of learning algorithm we're going to use. So sometimes we're going to use binary, as I said. It could be categorical. We're going to call these algorithms multi-class classification, where you have to choose between one of 7 categories. Think about taking a text document and classifying it based on the topic, whether it deals with sport, finance, politics, and so on. So you'll have a bunch of topics, and you want to classify the text document as being relevant to one of them. But you can also think about other things. You can think about sequences as output. I gave the example of part-of-speech tagging, where given a sentence, what you want to produce is a sequence of part-of-speech tags, noun, verb, adjective, and so on. You can imagine trying to produce a tree, say a parse tree, and you can imagine many other things that we're not going to deal with so much. One example of a structured output could be that you want to say something like ranking, right? So you want to rank your examples based on something, other than just choose the most positive or the most negative. So there's a lot of options here on what your label space is. In all cases, the fundamental operation that we're going to do is classification. And most of these other algorithms can be reduced in a well-defined way to a classification, moreover, to a binary classification. So this is going to be the key workhorse that we're going to deal with. And then later on, we're going to show, in some cases, how to do this reduction. Why is it okay for me to think about ranking, instead of thinking directly about ranking, to think about binary classification and then map ranking to binary classification. Same thing with multi-class classification and so on. So really, binary classification is going to be the thing that will carry us. And lastly, the model, right? So what is going to be this g of x that is going to map x's to y's? And we need to choose what kind of model we can learn. So let's start thinking about this. So here is a learning problem. I have 4 dimensions, x1 up to x4. Inside the box, there is an unknown function that you want to learn. and I'm going to give you the labels. Right? So it doesn't matter now what is the problem here, what is the kind of world problem. We abstracted it away, and now we have a learning problem. Here are 7 examples. This is the index, these are the features, and this is the y. These are the y's. What is the function? Yeah.
x4 and log x2.
x4 and not x2. Suggestion. Let's check if this is right. So you're saying that if x4 is on and x2 is off, then the example is positive, otherwise it's negative. Does it work? x4 is on here and here, and x2 is off. Positive example. The rest are negative. Works. Any other suggestion? No other suggestions? Yeah? x4 and x1 or x3. So again, we want x4 to be on, and we want either x1 or x3 to be off. Does this work? Is it the same function? It's not the same function. What do you mean when you say it's not the same function? It's consistent with the data. Right, so there are some examples, at least one, on which these two functions behave differently. So which one should I choose? Yeah. You don't know. Are there any other options besides these two? Yeah. Okay, I believe this is right too. Any other suggestions? What do you think? Each one of you, can each one of you come up with a different function that would be consistent with this data? How many functions are there that are consistent with this data? How many functions are there that we can consider? What did I tell you about the function before I continue with this question and make it more concrete? It's a function of 4 Boolean variables, and it's a Boolean function. How many functions are there? N? 2 to the 16. Okay, so let's think a little bit about it. We're going to So we want to try to learn this function. On these 4 variables, there could be 16 functions. Everyone agrees, right? 4 Boolean variables, 16 potential x's. My instance space size is 16. How many functions are there on 16 inputs? Each y could either be 0 or 1. Everything is possible. So I have 2 options for each row here. 16 rows, 2 to the 16 options, which means 2 to the 16 different functions. Quite a large number. But I gave you 7 examples. So not everything is possible, right? So I already fixed across from 7 rows here the label. How many functions are left? 2 to the 9, 512. So each one of you can choose 2.5 functions, and still they're going to be different, and we will not know which one is right. We don't have any way using this data to decide what should learning do. So just to summarize, there are 2 to the 16 possible functions. Hopefully you're convinced. And we cannot figure out which one is the right one. Even after I gave you 7 examples, there are still 2 to the 9 possibilities. What should we do? So is learning even possible? What are we doing here? So the real answer to this is the answer of hypothesis space. We are not going to consider all options. We're not going to be in this domain of complete ignorance, but rather we're going to make assumptions. Learning is about making the right assumptions, or pretty good assumptions, if possible. And specifically, the key assumption here is that of hypothesis space. What are we going to, what kind of functions are we going to consider? Specifically, okay, this is just a generalization of what we said. You all understand this. I can say, you know what, I don't care about all Boolean functions. I'm going to care only about conjunctions over 3 variables. So my functions, my target function, I assume is of this form: xi, nxj, and xk. So now I have a small hypothesis space, only 16 possible functions. Think a little bit about it and convince yourself. And I can write it down. So what I did here is I built a table of all functions of the form xi, nxj, and xk. And for each one of them, I gave you a counterexample that contradicts this function. For example, if you thought that it's x1 and x2, this contradicts it because there's a negative example here. So that's not going to work. This hypothesis space is not good because no member in this hypothesis space is consistent with the data. Here's another one. By the way, the same thing if instead of conjunctions, here I will have clauses, which are disjunctions. It's not going to work. No function is consistent with the data. I'm going to try something else. I'm going to try something that I call M of n rules, which means y is 1, the label is 1, if and only if at least m of the following n variables are on. Okay? So it's another Boolean type of Boolean function, class of Boolean functions. There are 32 functions like this for different values of m and n. N can be up to 4. And again, I have a table here. The notation means under the 2 of column, what I mean is that 2 variables out of this set, for example, out of 2 variables out of x1, x2, and 3 are going to be on. And what I put here in the index is the index of the example that is the counterexample for it. So again, you can go over it and check. And it turns out that there is no counterexample for this rule. So the function 2 out of x1, x3, x4 is correct. It's different than the 3 functions that you suggested, but it's correct. And because I decided that my hypothesis space is this M of n rules, that's my function. That's what I'm going to learn. So the important lesson here, which we're going to do all the time this semester, and I'm emphasizing it now because a lot of people that become experts in machine learning forget some of the basic assumptions. This is one of the basic assumptions. We're going to do this all the time. We are going to make assumptions on hypothesis spaces. So really, you can develop this general view of learning. Learning is really the removal of the remaining uncertainty. We are making assumptions, and under these assumptions, we're going to remove, using the data, the uncertainty that still remains. Right? So I didn't tell you which function it is. I told you, instead of considering 2 to the 9 functions, consider only this small space of functions. It's going to be tractable. Let's try to see what the data says about this set of functions. So we really say, suppose we knew that the unknown function is an M of n functions, or in other domains, or later on in the class, a different class of functions, but still a well-defined class of functions, and let's see what the training data does. So it really requires guessing a good, small hypothesis class, not as small as 32 here, and in fact could be even infinite, as you will see. Infinite but small, under some definition, good definition of small. This is going to take a few weeks for us to develop. But still, a well-defined hypothesis class, and then learn with it. But it's important to realize that we could be wrong. It's possible that we made wrong assumptions, and we need to understand what does that mean and how do we recover from it. Okay, so here is one of the other functions that you gave over there, and it's also a good function, but not in our hypothesis space. Okay, so hopefully this is important, and this really gives two kind of very general strategies. One is to develop flexible hypothesis spaces. Hypothesis spaces that really are completely expressive. Any function that you want, you could express with them. Decision trees, as we'll see in 2 weeks, is one like this. Neural networks is also like this, if it's large enough. You can think about nested collection of functions. So you start with a collection of functions. If you cannot fit any function in this collection, you grow it, and you keep on growing in a systematic way. This is one strategy. Another strategy is to say, you know what, I'm going to stick with a restricted class of functions. For example, only linear functions, or specific types of grammars, or some specific kinds of stochastic models. Not everything is going to be expressible using this class of functions, and we're going to figure out ways to survive despite the fact that the classes of function are small, like linear functions. Clearly, not all functions are linear. We're going to define this a little bit more carefully, and you'll see it, but many of you can maybe see what I mean. Why do we even consider it, given that it's not expressive enough? We're going to buy back some of the expressivity by augmenting our feature space, adding more features, and then learning linear functions over them. In either case, we're going to try to develop algorithms that find the hypothesis that belongs to this hypothesis space and fits the data. And then we hope that it generalizes well. And one of the things that we want to try to do in this class is to kind of quantify this hope a little bit and give some theories for when it's going to work, what kind of guarantees we can develop, and so on. Okay. So this is just a terminology, a summary of terminology that I already used before. So I'm just going to keep it here, look at it, make sure that we understand. And let's try to develop a concrete example within which we can actually suggest a learning algorithm. We may even suggest a learning algorithm today. So my running example for now is going to be one example that I showed on Tuesday, context-sensitive spelling correction. So given a sentence, I want to know which of the whether type 1 or whether type 2, belongs in this sentence. It's a binary prediction problem, and I want to make this real-world problem, spelling, or context-sensitive spelling, which is a little bit harder than just simple spelling. I want to make it a learning problem. So what do we do? Suggestions? We find features. That's indeed the first step that we're going to do. I just want to write this down more explicitly. We're looking for a function, f, that maps sentences to one of whether or whether. Whether type 1, whether type 2. That's our goal. And we're going to define the domain of this function, which is another way of saying what you just said. We want to find features. So here is an option. I'm going to suggest the following set of features. For each word in English, I'm going to define a Boolean feature, xw, that is going to be 1 if w is in the sentence. Otherwise, it's going to be 0. Okay? The property is clear. For each word, I have a dictionary of 1,000,000 words. I'm going to look at the sentence, and then this defines xw for each w. So in this case, I'm claiming that my dictionary is only size of 50,000. I have 50,000 words. When I look at the sentence, I check the 50,000 large dictionary, and I develop a point in a 50,000 dimensional vector space, right? Most of them are going to be zeros. And a few of them, the size of the sentence, are going to be 1, right? Is it clear what is my representation? So I have every sentence is becoming a point in a 50,000 dimensional space. Some points are going to be weather type 1 points because they belong to sentence that came with the label weather type 1. And some of them are weather type 2 points, right? Yeah?
What's this thing about if there's a W in the sentence?
So I have a sentence. The sentence is, I don't know whether to laugh or cry. I want to encode this sentence as a vector using my features. So what I'm saying is, this is my encoding. I'm going to look at the 50,000 candidate words in my dictionary. For each one, I'm going to ask, is it in this sentence or not? If it is, let's say the dictionary is indexed 1 to 50,000. If the first word in the dictionary is in the sentence, I'm going to put as the first feature, the first dimension of my 50,000 vector, 1. If it's not, I'm going to put a 0, and so on. This way, I have a unique mapping for my sentence to a vector of dimension 50,000. Okay? Yeah?
But in this mapping, do sentences.
Right? Very good point. So if I change the sentence to I don't know whether to cry or laugh, it's going to have the same mapping. Right? The same vector representation. So that's a price that I pay because I chose this representation. What would be another set of features that will get around this? Code the position. So for every word, I can entertain whether it's the first, the second, the third, the fourth, let's say up to 50. I don't deal with sentences over length 50 in the sentence. That's going to blow up the size of my features a lot, right? But I would get around this. So you will have to think in your real problem, you already see that there is a trade-off. As computer scientists, you can see that size probably eventually, when we can think about complexity, is going to mean complexity. Whether you want to pay the price of completely disambiguating the input and trading it off with a much larger space. So it's an important question. At this point, I just want to give an example. So I'm going to leave with this simple feature space. I'm going to show you another feature space in a few seconds, a real one. But what is clear now, this is our modeling step, is that we Okay, this is another interesting question. But before we get to it, we map the problem to this. Right? We have a vector space. We have weather type 1, the red points, weather type 2, the purple points. That's what we have. And now we want to learn a function. We want to learn a function that separates this data. And you agree now that there could be many, many functions that separate this data. Here is one. Separates the data perfectly. Here's another one. Doesn't separate it perfectly. Another one. Here's another one. So our job is to figure out which function do we love for this problem. And later on, how do we learn it? So we want to decide what function, and we want to define what is best, because I say here that best separates the data. What does best mean? And we already know, at least intuitively, that best is not going to be so simple just because of the example we had at the beginning of the class, where one suggestion was find a function that is consistent with your training data, and that was very easy for you to do. You just gave me back the table that I gave you. Here's a function, and it separates the data perfectly. And another one was the one with the second character being a vowel that separated the data no better than the first one, but you preferred it for some reason. The reason was that you had hopes that it's going to generalize better. The first function would have said no on any other name that is not in the list. The second function would say sometimes yes, sometimes no, better chance. So we'll have to define what is best. And this really goes to memorization versus learning, or accuracy versus simplicity, right? The first function was a lot more complicated, the table, than second character being a vowel. And of course, how well we're going to do it, on what data we're going to evaluate what best is. Probably just doing it on the training data is not going to be enough, because the learning algorithm saw the training data. So all these issues are going to impact the generalization that we're going to have. And of course, how to find it, we're going to get to it a little bit later. So here is a possibility that I want to entertain. I want to suggest that we're going to define the learning problem to be just learn a linear function that best separates the data. So I'm not going to consider this green curve, even though it's perfect. Instead, I'm going to just consider these straight lines, linear functions. What do I mean by linear functions here? Linear, I mean here linear in the feature space. So if X is my data representation, a vector, and W is going to be another weight vector, I'm going to call this the classifier. Linear function for me is going to be a function that is the dot product of X and W. Notice that I'm thinking about W as a column vector. So I'm going to, if I don't forget, it's going to be W transpose X. Sometimes when it's clear, I'm going to drop the transpose, but it's a dot product between vectors. And I'm going to make prediction based on the sign of this dot product. If it's positive, I'm going to say weather type 1. If it's negative, I'm going to say weather type 2. That's what I mean by a linear function. And I'm going to restrict myself for now to a linear function. And you could, of course, ask, why is it? I mean, it's not expressive. Most functions are not linear. But many functions are linear. And for example, so this is just a notational thing. Sometimes I'm going to write this as sign of dot product minus theta, which is the bias term. Could shift the dot product away from the origin. And basically, this is what we mean, right? This is just my definition or your definition for dot product. So I just want to convince you that many, many functions are linear functions. For example, all the functions we discussed earlier today are actually linear function. Conjunction is a linear function. Why? If you take this conjunction, x1 and x3 and x5, you can write it as a linear function. What does it mean to write it as a linear function? It means to give me a weight vector such that the dot product between x, a Boolean vector, x with x1, x2, x3, x4, x5, x6, times w is going to behave like a conjunction. Any suggestion? Why do I think that conjunctions are linear functions? What would the w be? In fact, you need to give me w and theta. All right? I want x dot w minus theta to be on when x1 and x3 and x5 are on, and off otherwise. Yeah? That would work, but it can be even simpler than that. It can be just 1, 0, 1, 0, 1 as the w, with theta being 3. So let's try it. So now I'm going to be given x. X is a Boolean vector, zeros and ones. If w is this, 1, 0, 1, 0, 1, do the dot product of w with x, and you will see that it's going to be 3 if all three of them, x1 and x3 and x5, are on. Otherwise, it's going to be less than 3. So the dot product minus 3 is going to behave just like a conjunction. Okay? So the reason I'm giving this example is so that you will realize that what we've done before is not very different than what we're going to do later. Really, these kind of simple rules or simple Boolean functions really are linear functions. We're going to deal a lot with linear functions. Not only that, even the m out of n rule that we had before is a linear function. What would you suggest here as your W? Okay.
Just a bunch of ones.
Where will they be?
Like images.
Theta has to be m. Right, so if I want, for example, at least 2 out of these 3, what I want is I want the W to be 1 on these variables, and theta has to be 2. And this way, if 2 out of these 3 variables are on, the function is on. If less than 2 out of these are on, it's not going to be on. Okay, so these are simple linear functions. It turns out, and we're going to see it later in the class, that probabilistic classifiers that people use a lot are also linear functions. So linear functions are actually expressive. And we're going to deal a lot with linear functions. Now, not everything is a linear function. Right? So, for example, XOR. Many of you have seen the function XOR. If you haven't, here it is. One version of XOR over 2 variables. These are not linear functions, so we will not be able to express them unless we do something. And I'm going to end this class with giving you an example of what are the things that we could do. So before we get to XOR, I'm going to look at this function. So some of you may have better intuition when we talk about real functions. So here is a function that labels some points blue and some points red. And I'm going to be able to learn a separator. Right? Learn a function that eventually I'm going to give it a point. It will tell me whether it's red or blue. If I want to do it with a linear function, not going to work, right? With some function, it will work, right? If I put this function, yeah, this works. But I'm restricting myself to learning with linear functions. What will I do? Yeah?
Absolute value of a shift.
Absolute value in a shift, okay. That's an idea, yeah?
Could be projected onto a higher dimension.
What does that mean?
Well, right now all the data is on a line.
And just x.
Yeah.
What will I do?
You want maybe put it on in terms of x.
I'm going to put it in terms of x and x squared. So the same function is going to look like this. Now a linear function is going to do it, right? So that's the trick that we're going to use all the time, right? So we are going to learn only linear functions because we know how to learn linear functions. But if we see that we're not expressive enough, just in this case, we're going to change the feature space rather than the function space. And the same thing is going to work also in the Boolean domain. When I gave you this XOR example, XOR looks like this, right? So positive examples on the diagonal, negative example on the other diagonal. No linear function separates them. What I'm going to do is I'm going to invent features that are conjunctive features, x1 and x2, x1 and not x2, and so on. And in this space, just like adding the x squared to the x, we will be able to separate it. Okay, so we didn't get to an algorithm. We're going to do this, in fact, in 2 weeks, because next week you're going to play with a real program that does learning. And we'll see you after that.
I sent you an email yesterday.